So today, guys, we are working through the knowledge we already had and just doing some practice with it to try and get the hang of using these identities as well as these trig functions. And we're going to start off with, we're going to take it a slight level up, working through what can be done and some of the thought process that might go through your mind when you're looking at these and how you might be able to kind of decide on what you should change and what you shouldn't. So I set up a small example at the very beginning. That is just to show what you start with, what you end with. That one is a little bit of a bonus for you guys to try and just see how that works out. But ultimately, we're going to start off with our very first question, which we have as sine of theta multiplied by cotangent theta plus tangent theta. And that is equal to secant of theta. Now, in this case, it isn't required that this is theta. This could be x. This is just a radian or a degree that is being plugged into this equation that is all the same throughout. So I'm going to set that up at the top so that we could always come back and look at it whenever we want to know what we started with. So in this case then, we're going to start working through what you might consider doing for such an equation. So right off the bat, you want to try and do any initial simplifications, any general arithmetic, just to try and simplify things slightly from what they are initially. What I mean by that is if we take a look at the right side, secant theta, that is one function, one trig function. So it's all right to leave it as is because we can turn that into the inverse of sine, work through it like that. But at this point, we shouldn't see a reason to complicate it just yet. Instead, we take a look at the left side, more specifically this multiplication of sine theta, and see that, okay, so we probably want to multiply, but before that, we have a cotangent and tangent. Let's see what happens on the inside of these parentheses because if we just multiply through, we'll just be tacking sine theta onto cotangent theta, and not a lot will change. So let's take a look to see what happens when we expand what's in the parentheses. So first things first is that if we're looking at cotangent theta plus tangent theta, let me see if I could, then we should remember what each of these represent, where cotangent is the inverse of tangent, and that tangent is sine over cosine, which means if we invert tangent, we'll be getting the reciprocal, meaning that cotangent is equal to cosine over sine as well. So let's plug these in for these values and see if anything changes. So here, cotangent becomes cosine theta over sine theta, and tangent here ends up becoming sine theta over cosine theta. Unluckily, if this was actually multiplication, we could see that these would cancel out and we would have no other issues, but since they don't, we can work through them as fractions and try and get them as one equation. But let's take a look back at what's outside the parentheses. If we recall, outside of these parentheses is sine theta, and we're multiplying. So in this case, we might use the distributive property. And the reason why I'm thinking of using the distributive property is because, well, now rather than two different functions as cotangent and tangent, two different ones from sine, we now have two variables that include sine in their part, in their function. So why not join together all of these sines into one equation rather than separating one off to the side? So that's why I'm thinking of doing distribution. Again, you can decide to set these to have the same denominator, add them together, and then continue the work that way. But me particularly, I'm seeing this as sine, as there's a sine, there's a sine, there's a sine. Now it's more conducive to actually combine together. So in this case, with the action of distribution, we would be multiplying sine theta by cosine theta over sine theta. And then we are adding this to the multiplication of sine theta times sine theta over cosine theta. And now on this left side here, we may be able to take notice that, well, if we have a sine in the numerator as well as a sine in the multiplication of the denominator, we have cross-like terms, so we could cross these out with 1 and 1 for each, leaving us with the left side as just cosine theta. On the right side, however, there is no crossing out that we could do, as we have a sine theta and a cosine theta. So instead, we'll just multiply straight across and work from there. So in this case, sine theta times sine theta, when you're multiplying something by itself, all you're doing is squaring it. So we could set that as sine squared theta over cosine theta. Now at this point, we've done quite a bit of work going through the left side, simplified it through a little bit. We still have the functions as separated, so we're going to work to try and combine them. But in the meantime, I just want to make sure to get some extra space going. So this is the work that we did to get us to this current point. I'll see if I can't keep it around for now, but just off on the side. There. Like that. There we go. And this work right here, we're going to bring up back to the top because we will be currently working with it. So now we want to combine these together as one term. And the reason I'm thinking of that is, well, if we take a look at the original function again, then our original equation, has secant theta over on the right all by itself. So we want to try and match that, or at least get close enough so that we can manipulate both sides to match it. And, well, two separate functions would not do that. So in order to get these as equal, we need to get the denominators as equal. In order to do that, we're going to have to manipulate this cosine theta to get a denominator of cosine theta. whenever we want to do that, well, we want to multiply this by something with cosine theta in the denominator, but so that it doesn't change our equation at all, we set this as cosine theta over cosine theta, because that is ultimately equal to 1, and when you multiply 1 by anything, it stays the same technically. So this would then give us cosine theta times cosine theta over cosine. And we are still adding that sine squared over cosine on the right. Now already you may notice that cosine times cosine would end up leaving us with a squared function as cosine squared. You may also notice that I am not regularly saying the theta. At this point then, I believe it should be understood that theta is a part of the function, and so rather than saying it 20 times, just understood that cosine squared has that theta next to it, that whenever I say cosine, there is that theta next to it. And what stays the same is the cosine in the denominator. And here now we have not touched this right function. At this point then, we have the same denominator. Whenever a fraction has the same denominator as another fraction, you could actually do the arithmetic of adding or subtracting that we have here. So we could just add these together as per normal, following through on the right, that we now have cosine squared plus sine squared over the only thing that actually stayed the same as cosine. Now at this point is when the identities should kick in, specifically the Pythagorean identity, that whenever you have a cosine squared added to a sine squared, that is the equivalent of 1. Remember that sine squared theta plus cosine squared theta is equal to 1 as one of our identities. So this numerator up top, we could just set as 1 over our cosine theta. And what does 1 over cosine theta equal? Well, it's the inverse of cosine, and another term for the inverse of cosine is secant. Hopefully in this case it was a little bit conducive working through. Again, there are so many ways that you could start. Instead of starting on the left, you could start out on the right, making it an inverse, seeing if there's anything you could do from there. Starting off on the left, you could directly multiply the sine theta. It's all about the direction you want to take it. Just first start off with any initial arithmetic, any multiplication, any addition that maybe you could do to expand out what's there, and eventually start canceling things out. Start substituting in for your identity properties. Start canceling out where we had previously the sine canceling out the sine, so that you could eventually simplify it enough so that you get your final answer. All right, so in this case then, we're going to move to our next question. Now, our next question here is 1 minus cosine over cosine theta over sine theta is equal to sine theta over 1 plus cosine theta. This is what we're going to be looking at. We're going to keep this up at the top so that we can constantly see it wherever we might need. And then box it up so that it's separated enough. All right, so now in this case, there is no direct arithmetic that you might be able to do. I see two paths in front of me. I see either we can take this 1 right here, and we could substitute that Pythagorean identity, so that we would end up with sine squared theta plus cosine squared minus regular cosine over sine theta. Now, in this path, you might think, well, there's 1, of course we do this. That's not necessarily the case, and mostly because typically whenever you substitute in this Pythagorean identity, you want to be able to cancel something out. Normally, you'd be able to cancel out the cosines because there's a positive and a negative, or the sines because there's a positive and a negative. In this particular case, because the cosine there is not squared, we cannot cancel them out, and so we would have to do a lot of extra work in order to get something out of this path. Our other path that may take just a little bit longer to see if you're not directly looking at the ones is instead that these fractions are very, very similar, almost reciprocals of each other. So why don't we cross multiply and see if maybe that gives us something to look at? So in this case, on the left, we'll have 1 minus cosine times 1 plus cosine. So 1 minus cosine times 1 plus cosine. And on the right, we're going to have the sine times sine. We'll do some of the simplification so that we can work through this and see if maybe this leads to something, which right off the bat, we can end up doing some simplification just from it, because we can notice that we could actually do some multiplication. We could actually, maybe this will actually lead somewhere that the other side did not directly do yet. So just like any other binomial, in this case, we have two terms, the 1 and the cosine, the 1 and the cosine, and so these become their own binomials, and we know how to multiply binomials using FOIL. So we would do first 1 times 1, leaving us with 1. Outer, 1 times cosine as a positive. Inner, negative cosine times 1. And last, where we have cosine times cosine, and any multiplication of a number by itself, whether function or not, is just squaring it. So we have cosine squared theta. And we could take that same information for sine times sine to show that this is just being squared on the right. Now we could see some cancelization, some like terms, as well as something we could actually work with, because here we have a positive cosine and here we have a negative cosine, and when you add together a negative and a positive of the same number, they cancel out. Excellent. So now all that's left on the left is 1, because we didn't do anything with it, we can't, and the minus cosine squared. Because there's no other cosine squared, we could simplify through with. And then we have the sine squared theta on the right. Now, my immediate thought is that I could see that there is a cosine squared, a sine squared, and a 1, regardless of whether we're adding, subtracting anything, and that immediately reminds me of the Pythagorean identity, where we have sine squared plus cosine squared is equal to 1. This order is just a little bit different. So we can try and set up the order so we have 1 on one side and the functions on the other. If your mind doesn't immediately remember those Pythagorean identities, what you can at least consider is to try and separate numbers and functions. So at the very least, you should try and get into the habit of ones should stay with the ones, and functions should stay with functions. In both cases, we would end up adding cosine squared because we need to do the inverse in order for this to cancel out here. And as always, what we do to one side, you do to the other, leaving us with the equation of 1 is equal to sine squared theta plus cosine squared theta, which we know as a Pythagorean identity as true. But if you wish to take it one step further, you can state that then 1 is equal to 1, and that is correct. So again, in this particular case, we don't immediately use anything fancy like having to substitute out some function like cotangent into cosine over sine or tangent into sine over cosine. We just directly go for the cross multiplication, and only after, not even after the cross multiplication, we're still doing the regular arithmetic until we get to the very, very end, where we just need to know that Pythagorean identity to say that, yes, this is in fact true. Now, our third question. This one ends up using a couple of the other functions that we may not necessarily normally use. So we have cosecant theta plus cotangent, make sure these t's look different, theta, and we are multiplying this by cosecant theta minus cotangent theta, and that is supposedly equal to 1. All right, so in this case, we should recall from just the previous example that we can multiply them together as if they were binomials, where in this case we have one term here in one binomial, and the same values, even though one is a subtraction on the right, on the other side as well. So this is a prime example for multiplication of binomials, which again, we just FOIL. In this case, we don't have a 1 to work with, and so our FOIL will be set up with mostly functions rather than having a 1 hidden inside, and so we may have to do some extra work afterwards, but for now, we'll just run through and see what happens. So in this case, we do first as cosecant times cosecant. At this point, we should know that multiplication of the same term is just the same as squaring it. Cosecant times cotangent, they don't mix, so we're just going to set them next to each other as a multiplication. And it is negative because a positive times a negative is negative. The inner, cotangent times cosecant, both positive, making it positive. So cotangent times cosecant. And then last, where we're multiplying cotangent times cotangent. And then one is positive, one is negative. This is just squared, but with a negative. So at this point then, I'm leaving the right side as just equal to 1 because although we can substitute this in for the Pythagorean identity, at the moment, we'd just be adding in extra functions that may just pollute the entire equation. Let's try and simplify things first if we can. So cosecant squared, if we look through, we don't see any other cosecant squared. So we're just going to drop this down as is because we can't do anything with it. Here we have a positive and a negative of cotangent times cosecant. And of course, when we have the same number as a positive and negative, we are able to cross them out because they cancel each other out. So those don't drop. And so we immediately simplify this equation into something much, much smaller. Now, after that, we have the negative cotangent squared theta. There is no other cotangent squared, so we'll just drop that down into our remaining equation. All that's left is to set the right side equal to 1 as it has been and see what we could do from there. Now in this case, again, we can take the 1 and set that up as a Pythagorean identity. 1 is quite a simple number to look at, work with, so for now, I personally am going to keep it. If you'd like to take the path of expanding that out and seeing what happens, by all means, perhaps you'll be able to work through it. In this case, I'm not going to disturb the 1 because I don't want to expand anything if I don't necessarily have to. On the left side, however, it's not that I have to, but we know that cosecant squared is not its original form, and cotangent is not in its original form either. That's because we should remember that cosecant is just the inverse of sine, and cotangent is just the inverse of tangent, which we could write as cosine over sine. So let's get these into as close to their originals as possible. So in this case, cosecant squared ends up as 1 over sine squared. And cotangent squared becomes cosine squared over sine squared. These will be equal to 1, and then we could work from there. What I notice is that both of the denominators are the same. So we can actually combine these together by the subtraction without any issue whatsoever, which would leave us with a cosine squared at the top over we would have a 1 minus, you don't want to forget about that 1 ever. We are not multiplying in this case, we are subtracting. 1 minus cosine squared theta over sine squared theta. Now in this case, I'm not particularly fond of fractions, as I'm sure you guys aren't as well. So I'm going to take this function over here, and let's get rid of this fraction. And one of the ways that we get rid of fractions is by multiplying them out. So if I multiply this by sine squared theta over sine squared theta, because this is the same number over itself, and that would be equal to 1, not changing anything, but still canceling just, in this case, we're not actually setting it equal to 1, my mistake. we are just multiplying by sine squared theta because we want to cancel these out. And what you do to one side, you do to the other. And 1 times any number gives you that same number. So now we are left with the equation 1 minus cosine squared theta, which is equal to sine squared theta, which is very reminiscent of exactly what we were looking at in the previous question, such that this is just the Pythagorean identity in a different form. And we all know what we did there. We added cosine squared theta to both sides to give us 1 is equal to sine squared plus cosine squared, which is just 1 equals 1. It is quite important to get a handle of just the general arithmetic, thinking of these as their own variables, because they still work the same way any other number, any other variable would work. They're just considered a function rather than an individual number. Now, our final example is one that's a little bit larger, which is why it ended up with its own page on the slides. And so there might be a little bit to write through, but we're still going to go through it. In this case, we have a secant minus a cosine over a secant plus a cosine. And that is equal to sine squared over 1 plus cosine squared. Now, in this case, it's difficult to necessarily directly understand which side we want to start with. Now, whichever side you do start with, absolutely, you are not wrong. Just work through it, and eventually you'll be able to get the exact same answer. It's just a matter of what you do and how you do it. Now, we can decide to cross multiply. We could see what happens there just like before. I'm seeing that this could possibly be a little complicated just because we would end up with something along the lines of secant theta plus secant cosine squared minus cosine minus cosine cubed theta. And so that's just first, outer, inner, last of the numerator and denominator going across. So I'm just seeing that since they don't have the same terms within their binomials, this can get a little bit more complicated, and so we're going to hold off on that and see if maybe we could do something to simplify some of these terms. Now, let's focus up on the left side for now. So seeing this left side, perhaps there's a way we could work with it so that it becomes simplified just as is. So in this case, something to remember is that in the case of secant, secant is just the inverse of cosine. And we have a cosine in the equation, so let's substitute that in as the inverse so that at the very least it's all cosines. We don't have any other functions on the left. And let's see if maybe something might pop into our mind there. So in this case then, the first secant becomes 1 over cosine. And we are adding cosine. Then, as our denominator, we have the second one, which is just 1 over cosine plus actually, sorry, the top one, the numerator is minus. We don't want to forget that. And the bottom one is plus cosine. So at this point then, we've got all cosines. We could try and work these out. Well, in this case, in both the numerator and denominator, we have a fraction being added to or subtracted to a whole number. So what if we wanted to try and actually combine them? Since they're both cosines, they should be able to combine much easier. In order to do that, we'd have to multiply this side by cosine over cosine. Sorry. We will be multiplying by cosine over cosine, but in this case, we also need to work at the entire fraction as a whole. So we have two options. We could either try and multiply this cosine on the right by cosine over cosine, or if we take a look at the fraction as a whole, rather than each individual numerator and denominator, what if we multiplied the entire fraction by cosine over cosine? Now, when I say that, all that would end up happening is we split this up into two parts, the numerator and the denominator. So the numerator function ends up having a cosine being multiplied by 1 over cosine minus cosine. And if we simplify this out, we have the cosine times 1 over cosine, and all that would do is you would set it over 1, multiply across, and you would end up with cosine over cosine. On the right, you would be multiplying cosine by negative cosine, which a positive times a negative leaves the minus, and multiplying by the same term would just square it. And we should note that any number over itself is just 1. And on the right side, we'd also be multiplying by cosine. Now, do note, because we are multiplying by cosine over cosine here, which is equal to 1, we're not changing anything within the equation in terms of values. We're just changing how it looks. Which is why we could do this, which is why we're going through the separation and seeing what we end up as our numerator, here being the numerator, and over here being our denominator. It's almost like a zoomed in view of each one separately before we combine them back together. So in this case, we would be multiplying again by 1 over cosine theta, but in this case, we're adding cosine on the right here, and this would give us with a similar equation as the numerator, being that we would have cosine over cosine plus cosine squared, where it would be positive. Again, noting that this particular fraction is equal to 1. Now we expanded it. We want to bring it back together. And in order to do that, we'll bring this over to the side a little bit so that it could stay there, but so our work doesn't disappear, but we have some more room to work with. Now in this case, we are able to find out that our numerator now is the equivalent of right here 1 minus cosine squared, and our denominator here is the equivalent of 1 plus cosine squared. Now at this point we have two paths. I'm going to bring back the sine squared theta that we have from our original equation over the 1 plus cosine squared. Now at this point then, we now have a common ground between our cross multiplication, so we can actually cross multiply the 1 minus cosine squared times the 1 plus cosine squared, but I'm actually seeing something a little different. If we look at both of these equations, both of these sections, well, the numerator is 1 minus cosine squared theta on the left, and the right we have sine squared theta. Nothing in common there, but if we take a look at the denominators, well, then we have a 1 plus cosine squared and a 1 plus cosine squared, meaning that they have the same denominator. That's half of our equation down of what we need to set equal. So then how can we somehow change 1 minus cosine squared to equal sine squared? Well, we need to somehow get rid of this cosine squared. We need to somehow add in a sine squared, get rid of the 1. Well, at this point then, we should perhaps click together that what does 1 become in terms of our fraction, in terms of our functions? 1 is the equivalent of sine squared, which gives us our sine squared, and a positive cosine squared as well. So, although it adds in an additional function rather than just sine squared, it does help because we now get a positive to our negative. And when a positive and negative of the same terms meet, they cancel out. So all that's left is sine squared is equal to sine squared, which we bring back to our numerators because our denominators stayed the same as just 1 plus cosine squared and 1 plus cosine squared, being that these two are equal and are in fact, and that verifies our equation. Now this one was a bit of a long one, especially since we had to use secant and manipulate some of the equation before we did any other multiplication. And I'm sure it was probably a little bit confusing when we got into the fraction here. Feel free to try out separating each one first, and then simplifying each one separately, where you take the 1 over cosine theta minus cosine and the plus cosine to see how you could simplify those without seemingly multiplying the entire fraction here. And so you should be able to get something very, very similar, but hopefully you guys were able to kind of follow along. At the very least, if you found a different way and were still able to verify that they are correct by setting them equal to each other, excellent. It's a big exercise in how to work around some of these functions with the information you have. And now that we're going to be working with more identities, more information for each of these, then the paths will begin to grow in what you could do. So just try and find something that works for you as well as just clicks, because this sort of thing is very important about you taking your mind and setting up connections with your information. You see a 1, go straight for those Pythagorean identities. See if that works. You see a chance for cross multiplication. See if maybe that might give you an easier route. If you see the inverse functions, see if maybe by changing them into their original sine, cosine, and tangents, if that makes anything easier, and so on and so forth, just trying a few different pathways that may give you the route that you want. Ultimately, guys, I hope that you're enjoying your day. Stay safe and healthy.